These are the corrections for question 4 of the midterm homework. First of all, some radioactivity revision. Question A, what is an isotope? Those are atoms of the same element, so meaning that they have the same proton number or the same number or the same atomic number or the same number of protons, but they have a different mass number, meaning that they have different numbers of neutrons. B, the carbon-14 isotope is a beta particle emitter. What is a beta particle? A beta particle is an electron that has been emitted from the nucleus. Now, it's important to specify where it has come from because usually electrons don't come from the nucleus. Just as a bit of revision, a beta particle or beta radiation is produced when a neutron from the nucleus splits up into a positive proton and negative neutron. The proton stays in the nucleus, the electron is emitted. List 2 properties of beta particles. So, first of all, if we can't remember exactly the properties of a beta particle, we know that they're just made up of an electron. So first of all is that it's going to have a negative charge. Second thing we could say is that it has a negligible mass. So meaning that its mass is practically zero in comparison to a proton or a neutron, or in comparison to the atom it's being released from. Next, then a beta particle is more penetrating than an alpha particle. You could also say there that it's less penetrating than gamma radiation. It's also faster moving, so it moves at a high speed. In comparison to alpha particles, but again slower moving than gamma radiation. Beta radiation, it can cause damage or mutations to living tissue. And if we come back again and think about it as an electron, we know from chapter 2 where we studied cathode rays, which are just streams of electrons, that it's deflected by a magnetic field or an electric field. So again here, this didn't really require you to have any knowledge of radioactivity actually, because a beta particle is just an electron. So if you had some information about an electron, that would get you full marks here. So any 2 of these for 6 marks. Next, writing our equation. So carbon-14 looks like this, carbon-14, and its atomic number is 6. What we are changing about this is we are removing a neutron and making a proton and an electron. And so that electron is going to be sorry, I wrote that wrong. That electron is going to be emitted from the nucleus. So that's my beta particle. You could also write that as 0, -1 and the beta symbol. Either one of those is correct. And you'd get 3 marks just for having the beta symbol correct there, either one of those. And so what happens here, the mass number doesn't change, because even though we've lost a neutron, we've gained a proton. So the mass number doesn't change. The atomic number does. That increases by 1 because we have 1 extra proton. And if I look at my periodic table, the element that has the values 14 and 7 is nitrogen. So my balanced equation there is that carbon-14 emits an electron or a beta particle, and I get nitrogen 14,7 being produced. Last one is a bit cheeky because it's not actually part of this chapter, but we'll have a look at it anyway. So calculating the relative atomic mass of a sample given the mass spec information. So how we're going to approach this, we will say that since we've got percentages, we will say that these values correspond to how many atoms of each isotope we would have in a sample of 100. So that would mean that to get the total mass, we would do 90.9 multiplied by 20 plus the 0.3 by 21 plus 8.8 by 22. So you'll see in the question there where I'm getting those values. When I add all of that up, I get 2017.9. So that's the mass of all 100 of the isotopes. In order to get the average mass, then I have to do 2017.9 divided by 100 to get the mass of 1, which gives me 20.179. Which is very, very close to the value on the periodic table, so I can be quite confident in my answer there. Part F moves on to revising periodic trends. First of all, defining first ionization energy. It's the minimum energy required to remove the most loosely bound electron from a gaseous atom in its ground state. So those are the key things we need there for this answer. It's worth 5 marks. So minimum energy required to remove the most loosely bound electron from a gaseous atom in its ground state. Part 2, account fully for the trends in first ionization energies of elements across the second period. So across a period, we know that ionization energy increases. So that's my general trend. And the reason for that is due to the increased effective nuclear charge. I'm just writing it shorthand here. Increased effective nuclear charge and our decreasing atomic radius. So when I see that this is worth 12 marks here, and I've only given 3 bits of information, I'm probably going to need a bit more. And what I'm going to do here is explain the exceptions. So across period 2, we have some exceptions. Going from beryllium to boron, it decreases, and going from nitrogen to oxygen, it decreases. So we just want to explain why that is. And that's because we have increased stability. So the up arrow means increased stability of atoms. In this case, beryllium and nitrogen. The increased stability of those because they have a full or half filled outer shell. So anything that has a full or half full outer shell has increased stability, meaning that more energy will be required to remove that electron. Part 3, account for the trend in first ionization energies of the elements going down period 2, or group 2, sorry, group 2. And here our trend is that they decrease due to the increased atomic radius and the increased screening effect of the inner electrons. So there's an extra shell added each time you go down the group, meaning that there's more electrons closer to the nucleus that are shielding or blocking the positive attraction that the nucleus has. Now, instead of saying increased screening effect, you could also word that as decreased effective nuclear charge. And those mean the same thing, that the outer shell electrons have less of an attraction to the protons in the nucleus because they're shielded from it.